All right, good morning, everybody. William, can you guys hear me okay?
Yeah, we can hear you.
Great. Nice to see you all. A couple quick announcements before we get started. So just as a reminder, your Chapter 2 quiz is today. You can take it in any 1 hour period. It's posted in Moodle and it needs to be submitted before midnight. So keep that in mind. This week we are moving into Chapter 3, so a new chapter where we will more formally look at derivatives. So Chapter 2 really laid the groundwork for what a derivative is and what we want to do with it. And Chapter 3 says, well, how can we make this a little bit easier, a little more straightforward to be able to use and apply? So that's sort of where we're going from here. Yeah, so let's get started. Let me switch over to my document here. So at the end of Chapter 2, we started thinking about derivative formulas, and we did this graphically. We said, okay, if we have a graph of the original function, how do we graph the derivative function from the original function? And we thought about what that meant in terms of rates of change and things like that. And so in math, one of the things that we often do is we look for patterns, right? So when we have patterns, we can then sort of more formally think about them and look for exactness and turn them into formulas. And so that's what we're going to be doing in Chapter 3 is we're going to be learning some formulas for derivatives algebraically to talk about the function. So we already know how to do this graphically from Chapter 2 and on a table from Chapter 2, but now we want to do this algebraically. And these formulas are based on the definition of derivative. And so if we're being really precise, the definition of derivative looks like this. The limit as h goes to 0 of f of x plus h minus f of x over h. So we know a little bit about limits, and f of x plus h is a composite function. So if we have a particular function, we could set this limit up to find the derivative formula. Now, we are not going to be using limits to find this for the most part, but instead we're going to appreciate how these limits lead us to the formulas we will be using. So there's a couple of examples here of just how this limit works to get some of the formulas. I'll just talk through briefly with you about what they look like. But again, this is just to show you how we got these formulas that we're going to be using. So for example, if we have a function that is a constant, right? So f of x equals 10, f of x equals 30, whatever that number may be. If we were to apply the derivative formula, we can't even plug an x plus h into a constant. It's still that constant no matter what. So we end up with the limit as h goes to 0 of c minus c. And we know that if you subtract the same thing from itself, you get 0. So you have 0 divided by something. And it doesn't matter what that something is as you get closer and closer to 0. That's always going to be 0 because 0 divided by 1 is 0. 0 divided by 0.1 is 0. So on and so forth. So what that tells us is that for any number, the derivative function is going to be 0. So that allows us to have a formula to the effect of if f of x is a constant, then the derivative of that function is always 0, right? And so we're generalizing this for any constant. That's what the limits allow us to do. So there's another example here of a linear term, mx. You can sort of follow the algebra to see that ultimately we get that the derivative is just m, the slope of that linear term, right? And the idea is that if we were to apply this limit to all sorts of different polynomial terms and eventually power terms, we end up with a formula that looks like this. So if f of x equals x to the p, then f prime of x equals px to the p minus 1. So what does that mean, right? So f of x equals x to the p. So that means you have an x and then you have some power up here. So let's say 32, right? It can be any number because this is true for polynomials and power functions. Polynomials are when you have integer powers, and power functions are when you have like x to the 1/4 or x to the negative 2/3, right? But if x is in your base and then you have some power up here, the general formula to find the derivative algebraically is that the power comes down to the front, so 32x, and then we subtract 1 from the power. So 32x to the 31. Okay, so this is called the power rule. And today we're going to be looking at the constant rule, the power rule, and then later on sine and cosine. And we're going to be practicing all the different types of things we can do with this formula. And so I want to point out that the reason we are able to now use these formulas is because we did all that work in chapter 2 to really understand what a derivative is graphically on a table at a point with limits and do all that background work so we understand that the derivative is the rate of change at a point, right? When we find a derivative function, that allows us to plug in any x value to get the rate of change at that point. Okay, so what do we do with this? So here's just a summary of the 3 rules we have. If your function's a constant, the derivative is 0. So notice that the constant is by itself. It's not touching any x's or any functions. It's just a standalone number. If you have a linear term, right, so you have a number times x, the derivative is just that number. And if you have x raised to some power, the derivative function says the power comes down out front, and then we subtract 1 from the power. So we are going to practice these 3 rules, okay? We have a through g functions here. And what I'd like you to do is I'd like you to take 2 minutes to try to figure out which of these 3 rules is going to apply, and then figure out what the derivative of each of these functions will be. Okay, so remember, it's the derivative function that we are finding for each of these. Okay, so take 2 minutes, try to apply these rules, and then we'll go through it together. All right, take about 30 more seconds. All right, so let's take a look at these. So the first one here, we have f of x equals 7. I notice that there's no variable there. It's just the number 7. So I have a constant that's by itself. And so according to my rules, that tells me that the derivative is going to have to equal 0. For the second one, I also have a constant, 10. However, that 10 is attached to an x. And so as soon as a variable is in the problem, it's no longer going to be 0, right? So instead, I come over here to my linear term. If I have 10x, the derivative should just be that 10, okay? So it's really important to notice the distinction between A and B, where this one, part A, has a constant by itself, whereas part B has a constant attached to an x, because those are going to lead us to different results, okay? For part C, we're using our power rule. So we have x squared. So the power rule says that the 2 comes down, and we're going to subtract 1 from the power. So I get 2x to the 1 power. Now, we don't have to write the 1 power. It's up to you if you want to, but we can also just write that as 2x, okay? For the next one, we have x to the 5th. So again, we're going to use that power rule. The 5 is going to come down, and we're going to subtract 1 from the power. So we get 5x to the 4th, okay? So for part E, F, and G, we end up with powers that are a little bit more tricky algebraically. So we have to be careful when we're dealing with negative powers, with fractional powers, or negative fractions. So here we have x to the negative 4th. So what we're going to do is we're going to bring the entire power down to the front, which includes the negative. So whatever's up there has got to come with it. So I get negative 4x. And now if you do negative 4 minus 1, you're going to get negative 5. So it becomes more negative. So we have to be a little bit careful about that. Okay. For the next one, we have x to the 2/3. So again, the entire power comes down to the front. So I have 2/3 x. Now I'm going to subtract 1 from the power. So 2/3 minus 1 is going to give me negative 1/3. So if you have a fraction that's less than 1 and you subtract 1, that's going to mean that your power is going to become negative. Finally, we have x to the negative 4/5. So again, the entire power comes down out front. So negative 4/5. And then we're going to subtract 1 from this power. So negative 4/5 minus 1 is going to give me negative 9/5. So again, whenever your power is negative or a fraction, you just want to be extra careful when you're doing the subtraction part of the power rule. Okay, so that's sort of Formula 101, right? So that's like the basics. That's the most basic way that we're going to see these types of terms, right? But now we can add on to it and we can start doing different things. So the next rule that we're going to add on is called the constant multiple rule. And so that says that if you take the derivative of a function that is multiplied in front by a constant, that when you do that, you're going to get that constant times the derivative of the function. Okay, what does that look like and what does that mean? Okay, so let's say we have 5x cubed. Okay, so what we've looked at so far is x cubed. What does that 5 do? So much like the 10 up here, if the number is attached to a function, then it becomes part of the derivative. Okay, so the constant multiple rule says that if your original function has a constant multiplied, that constant, that 5, will multiply the derivative of the function. Well, the derivative of this function is 3x squared, right? X cubed becomes 3x squared. And so we can simplify this by multiplying the 5 and the 3 together. So we get 15x squared. The way we usually think about this is that when the 3 comes down, when we're taking the derivative, it will multiply whatever is in front. But what's important is that if there's a constant in front, that doesn't make the derivative 0. The only time it's 0 is if the constant is entirely by itself. So again, if the constant's in front and it multiplies the function, when the power comes down, it multiplies that constant, and then we subtract 1 from the power. Okay, so we're going to practice this with some examples that have constants in front. So here, this is pi. Pi is a number. It's approximately 3.14. And then here you'll see various powers. Again, whenever you have negatives or fractions, you need to be extra careful when you're subtracting 1. But I want you to go ahead and try these using this constant multiple rule, just remembering that whatever number is in front needs to multiply the derivative of the function. Okay, so take about 2 minutes, try these out, and then we'll go through them together. All right, take about 30 more seconds. All right, so let's take a look at these derivatives now that we've added in our rule about having a constant. So for the first one, this one's a little tricky, right? Notice that there's no x here. It's just pi, which means this is a constant that's by itself. And therefore, the derivative of that first one is going to be 0, right? So again, we're trying to get comfortable recognizing different patterns in the functions we're working with so we know how to apply the derivative. For our second function here, we have 4x cubed. So the 3 is going to come down to multiply the 4 to give me 12. And we're going to subtract 1 from the power. So we have 12x squared. For our third function here, we have a 20 up in the power. So when we take the derivative, the 20 comes down to multiply the 9. So I get 180x to the 19th power, because again, 20 minus 1 is going to give me 19. The next function, I have negative 3x to the 5th. So this negative is part of this constant, so it doesn't disappear. So when the 5 comes down, it's 5 times negative 3. So I get negative 15x. Now I subtract 1 from the power. 5 minus 1 is 4. Okay. For part E, we have 6x to the negative 6. So the negative 6 comes down to multiply the positive 6, and we get negative 36x. And then we have to subtract 1 from the power. So negative 6 minus 1 gives me negative 7. For part F, I have 6x to the 1/3. Okay, so the 1/3 is going to come down and multiply the 6. 1/3 of 6 is going to give me 2x. We subtract 1 from the power. So I have 1/3 minus 1, which is going to give me negative 2/3. Okay, again, be careful with fractions up in the power. And then the last one, we have 7x to the negative 2/5. So negative 2/5 comes down to multiply 7, giving me negative 14/5 x. Now negative 2/5 minus 1 is going to give me negative 7/5. Okay, so we want to make sure we get really comfortable with fractions. If it's been a while since you've done them and you need some help thinking about them, you can certainly stop by office hours or drop in help, and we're happy to go over fractions with you. Okay, so that's the constant multiple rule. Now, the next thing we need to talk about is the fact that we need to have things in the form x to the p to use the power rule, right? To use this rule that the derivative is px to the p minus 1. Sometimes we have functions where we want to use this rule, but in order to be able to use it, we have to use some algebra to rewrite the function first. So it's not written in the right form, but can be put into the right form by using what we remember from algebra. So for the next example that you're going to try, there's going to be 3 problems where you're going to need to think about how we can algebraically rewrite these functions to be in this form where x is in the base and then it's raised to some power. Now, the reason that we're doing this particular problem is because students often forget how to do this. And so this is sort of the reminder of sort of the key ones that come up, okay? And so here we have 3 different functions that need to be rewritten. We have the square root of x, we have 4 over x cubed, and we have the 5th root of x squared. So each of these needs to be rewritten first into the form x raised to some power before we can take the derivative. And I will mention that you cannot take the derivative of x cubed while it's down in the power. So you got, or down in the denominator. So you got to get it out of the denominator before you can take the derivative. Okay, so I'm going to give you about 2 minutes. I want you to try this out, see if you can remember. If you can't, that's totally fine. That's why we're doing it, because oftentimes people forget. But try it out. See if you can remember how we might rewrite this first, and then how we take the derivative. So after about a minute, I will do a rewrite. And so if you didn't remember that part, you can then go ahead and take the derivative from that step. But we'll go over it together in about 2 minutes. All right, so let's take a look at these. So first, let's talk about the rewrite for each one and then the derivative after we talk about the rewrite. So let's start with the square root of x. Whenever you have the square root of x, the square root is a symbol that represents the 1/2 power. So in order to be able to use the power rule, we need to rewrite the square root into x to the 1/2. So that's the rewrite there. Then after we do the rewrite, we can go ahead and take the derivative. So the 1/2 comes down in front, and we subtract 1 from the power. So we get 1/2 x to the negative 1/2, okay? And so again, as a reminder, be really careful with fractions that are up in the power when you're subtracting 1 from the power, okay? For part B, we have 4 over x cubed. If we want to get a term out from the denominator, we can bring it up by changing the sign of the power. So 4 over x cubed becomes 4 times x to the negative 3. So notice that the power has become negative to bring it up. But now this is in the right form to use the power rule. So once we've done that, we can take the derivative. The negative 3 will multiply the 4, giving me negative 12x. And we subtract 1 from the power, so to the negative 4. And then finally, the last one, we have the 5th root of x squared. So when you have a number in the root symbol, that changes it from a square root to a different type of root. And so whatever was inside gets raised to 1 over whatever that number is. So we can write this as x squared to the 1/5 power. And if you have a power raised to a power, you can multiply those two numbers together. So we can rewrite this as x to the 2/5. And then we can take the derivative because now this is in the right form. So we get 2/5 x, we subtract 1 from the power to the negative 3/5. One thing I want to caution you about is that sometimes people will rewrite the function and forget that they still need to take the derivative. These are two different steps. We don't always have to do this step. It depends on if you have to rewrite the function or not, but rewriting the function is not the same thing as applying the rule for the derivative. So just keep that in mind, okay? Don't forget to actually do the power rule after you've rewritten, okay? So now we know basic formulas, we know the constant multiple rule, we've practiced rewriting. So the next part that we're going to bring in is what do we do if we have a bunch of terms instead of just one that are separated by addition or subtraction? Okay, so if you have one function plus another one and you want to take the derivative, you can take the derivative of the first function plus the derivative of the second function. And this is also true for subtraction, right? So what that means is if you have a function that is separated by addition and subtraction, you can take the derivative of each piece independently and just put them together. So what does that mean? So these are the 4 problems we're going to be looking at. That means we can take the derivative of x to the 5th minus the derivative of 2x squared plus the derivative of 6x plus the derivative of 1 to get the derivative of the entire function. It just means we can go term by term and take the derivative of each piece to get the entire derivative of the function, okay? So it doesn't really change much to the other stuff we've been doing. It's just remembering which rules to use and then putting them together, okay? So I'm going to give you about 3 minutes to try out these ones. You'll notice that for B, C, and D, you also have to rewrite the function before you can take the derivative. But otherwise, we're still just practicing all those rules, sort of putting them together, okay? So take about 3 minutes, try that out, and then we'll go through it together. All right, take about 30 more seconds to finish up wherever you're at. All right, so let's take a look at these. So for the first function, we don't need to rewrite it. There's nothing here that's not already in the correct form. So we can go ahead and take the derivative by just going term by term. So we start with an x to the fifth term. And so the 5 comes down in front, and we subtract 1 from the power. So we get 5x to the fourth. The next term, we have minus 2x squared. The 2 comes down to multiply the 2, and we get minus 4x to the 1. Again, you don't have to write the 1 power. You can if you want. 6x. So this is the special rule. That's a linear term. And so if you have a constant times just x, the derivative is just that constant. And then finally, the derivative of 1, notice that it's not attached to any variable. So the derivative of that is just going to be 0. And again, you don't have to write the plus 0. I'm just writing it right now so we can see how each term maps up to the original function. Okay. Now for part B, we do need to rewrite first because we have the square root of x, and we need to turn that into x to the 1/2. So I did that rewrite, and then from there, I can go ahead and take the derivative term by term. So I have 3x cubed, so the 3 comes down, so I get 9x squared minus, now the second term I have x to the 1/3. The 1/3 comes down, and I subtract 1 from the power. So 1/3 x to the negative 2/3. And then finally, the last term, I have x to the 1/2. So the 1/2 comes down, and I subtract 1 from the power. So I get 1/2 x to the negative 1/2. So again, I had to rewrite that first, but then I can just take the derivative term by term, trying to be extra careful with my fractions. For part C, I also have to rewrite this. So this is my rewrite. 10x to the fourth stayed the same, but here the fourth root of x becomes x to the 1/4. And then 2 over x cubed becomes 2x to the negative 3. I needed to bring that up from the denominator in order to be able to work with that. So once I've rewritten it, I can take the derivative term by term. So for the first term, the 4 comes down to multiply the 10, and I get 40x cubed minus, now I have x to the 1/4. So here the 1/4 comes down, and I subtract 1 from the power. So 1/4 x to the negative 3/4. And then finally, the negative 3 comes down, and I get negative 6x to the negative 4. Okay, so again, I still have to take the derivative after I rewrite, and I have to be careful as I go, but as long as I'm careful, I should be able to find the derivative of each piece. Last but not least, I needed to do a rewrite because I have a square root here. So I rewrote that as 2x to the 1/2. So here, the first term, I have negative 3x to the negative 3/4. When the negative 3/4 comes down, the negatives are going to cancel, right? And I'm going to get 9/4 x. And then when I subtract 1 from the power, I get negative 7/4 plus. Here, when the 1/2 comes down to multiply the 2, that's going to give me 1x, and now I subtract 1 from the power. So I get 1x to the negative 1/2. Again, you don't have to write the 1, but you can if you'd like to. So again, we're able to get the derivative function by rewriting and then going term by term. I do want to remind you that the derivative function allows us to plug in any number and find the slope of the tangent line at that point. So even though we're getting a function, the use of it is to be able to plug in a number to get the slope of the tangent line. Okay, so adding on to our power rule, we're just going to keep adding things on that all have to do with the power rule here. The next thing we want to talk about is the second derivative. So we talked about the notation of this, right? F double prime of x is typically the way that we see this. How do we put this into practice? we're going to apply the power rule 2 times to the original function. Okay, what does that mean? Let's look at a very quick example. So let's say we started with the function 3x to the 5th. Okay, we know from all the work we've been doing earlier today that the first derivative is going to be 15x to the 4th. So the 5 came down and multiplied the 3, and then I subtracted 1 from the power. If I wanted to find the second derivative, I would need to do the power rule again, but I would do it to the first derivative, right? So I would go ahead to the 15x to the 4th, and now the 4 will come down to multiply the 15, giving me 60, and subtract 1 from the power, 60x cubed. So I'm applying the power rule 2 times, once to go to the first derivative, and then again to go to the second derivative. Okay, but the power rule works the same way to get to the second derivative. So I'm not doing anything too crazy to go from understanding the first derivative to the second derivative. Okay, so let's try an example with some second derivatives. Okay, so for each of these, I want you to find the first derivative and then the second derivative. And you'll notice that for A and C, you're going to have to rewrite them. Okay, and for part B, that one's a little tricky. Try to figure out what that E, where it is and what it means. So remember, E is a number, 2.71 approximately. So think about how the power rule might apply to part B. Okay, so again, for A and C, rewrite first, then find the first derivative, then find the second derivative. And for part B, think really carefully about how the power rule applies. So I'm going to give you about 3.5 minutes, since you're doing 2 derivatives here, to try these out. All right, take about 30 more seconds. All right, so let's go through this one. So for part A, I needed to rewrite this. Notice that the 3 over x becomes 3x to the negative 1. There's an invisible 1 power that we don't usually write, but we still need to get it out of the denominator to be able to work with it. So rewriting this is sort of the most crucial first step, making sure we get that right. So then we can go term by term. So the derivative of 6 is 0. So we can write that down just as a placeholder, so we're reminded that that's what the derivative was. For our second term, we have minus 3x to the negative 1. When the negative 1 comes down to multiply this minus 3, the negatives are going to cancel, right? So the 3 stays from the constant multiple rule. And now I need to subtract 1 from the power. So negative 1 minus 1 becomes negative 2. Then from the next term, the negative 2 multiplies the 3. So I get minus 6x to the negative 3. And then finally, plus, now the 1/3 comes down. So 1/3 x to the negative 2/3. So that's what my first derivative looks like. I feel like the trickiest part of getting to the first derivative is making sure you rewrite this correctly. So sometimes that takes a little bit of practice. So the more practice problems you do on that, the better off you'll be. Okay, now let's look at the second derivative. So again, we want to apply the power rule to the first derivative, right? So we'll ignore the 0. If there's nothing there, we don't need to deal with it. Here we have 3x to the negative 2. So the negative 2 comes down to multiply the 3, and I get negative 6x to the negative 3, because I'm subtracting another one from the power. Here, I have a negative 3 that's going to come down and multiply a minus 6. So the negatives are going to cancel. I'm going to get plus 18x, and now I'm going to subtract 1 from the power to the negative 4. And then here, I have a negative 2/3, which is going to multiply a positive 1/3. So I'm going to get minus 2/9 x, and then I subtract 1 from the power. So to the minus 5/3. Okay. So the most common mistakes that people make are losing negatives. That's like the place where people lose things. So be really careful when you're doing these that you're just not losing anything along the way. Okay. So let's look at part B. We have x to the e power. Well, remember that e is a number. And the power rule says that when you take the derivative of x raised to some number, that the number is going to come down in front. So the e comes down. And then we subtract 1 from the power. So that's going to become e minus 1, right? We're going to leave e as e because it's an irrational number. And so we just leave it and we write it as e minus 1. That's how we would represent the first derivative of this function. It's a little goofy, but we could do the same thing with pi, right? If we had x to the pi, it would become pi x to the pi minus 1. So we're just making sure we can apply this rule no matter what the power is. So now, when we go to the second derivative, we got to do the same thing. So the e from before is still there, but now an e minus 1 is going to come down in front. So I have e minus 1, e, x. Now I'm going to subtract another 1 from the power. So I have e minus 2, right? So again, this is just really meant to show you that you can apply the power rule even if the number is something that's not a traditional thing we look at, right? You could do something similar like, I don't know, if you had f of x equals x to the a, and we knew that a was some number, the derivative is ax to the a minus 1, right? You're just applying the power rule to whatever you're given. And if it's a number you know that's like an integer number, then we treat it like we have been. But if it's something that's a little more fuzzy, right, we just leave that thing as is. We leave e as e. Okay. So let's look at part C. So we did need to rewrite this square root into the 1/2 power. And so now we can take the first derivative of this function. So here we have 6x to the 7th. So the 7 will come down to multiply, giving me 42x to the 6th minus, Now, when the half comes down, 20 times half is 10x to the negative half. Okay. And then if we want to do the second derivative, we apply the power rule again. So we do 6 times 42. That's going to give you 252. And then we subtract 1 from the power. You can certainly do that on your calculator. I did 42 times 6. And then here, when the negative half comes down, it cancels out the minus. So I get plus 5x to the negative 3 halves. Okay. So finding second derivatives just means applying the power rule again. So if you get comfortable enough with the power rule, then going either to a first or second derivative should feel comfortable. But again, the parts that are tricky are when we have fractions and when we have negatives. So that's where we need to be extra careful when we're doing our work. Okay. So how are we doing on time? Okay. So let's look at the next example here. So we have the function 1/3 x cubed minus 2x squared plus 3x plus 1. And so there's a series of things that we're going to look at here that sort of link the stuff we're doing today with the stuff that we were doing back in chapter 2 and how these all relate and how doing these derivatives algebraically make our life a little bit easier. Okay, so you're going to be computing the first derivative. That's what we've been doing today. Then you're going to find the values where the derivative equals 0. So you have to set your answer in part A equal to 0. So that's algebra. So hopefully you remember how to do that. Then in part C, we want to know for which values of x is the original function increasing or decreasing. So this is linking back to chapter 2. How did we think about increasing, decreasing in relation to the derivative? Then you're going to compute the second derivative. That's what we were doing today. Find the values for which the second derivative equals 0. So that's algebra. We're going to set this function equal to 0 and solve. And then we want to link it to the concavity, which is what we did last time, where we talked about how the concavity is related to the second derivative. So that links back to chapter 2. So I'm going to give you about 3 to 4 minutes. If you're not sure what to do, definitely just start with A and D. That's what we were doing today. Find the first derivative and find the second derivative. Those are the formulas we've been practicing. Then, parts B and E, we're just setting those equal to 0. So hopefully the algebra works out. And then if you remember, you can try to link it up to these properties. Okay, so try it out and then we'll go through it together in about 3 or 4 minutes. All right, take about 1 more minute. All right. So let's go over this and see how we can take what we've been learning about these formulas to link back and understand better some of the stuff we were doing in chapter 2. So part A says to compute the first derivative. So notice here that I have 1/3 x to the power of 3. So when the 3 comes down, it's going to cancel out the 1/3, leaving you with just a 1x squared because we subtract 1 from the power. So we can write 1x squared as x squared. You can use the 1 or you can leave it off. Both are fine. The second term, the 2 will come down to multiply the -2, giving me minus 4x to the 1 power. The derivative of 3x, that's a linear term. The derivative is 3. And then the derivative of this plus 1, right? That's a constant that's by itself. So the derivative is going to be 0. So my first derivative is x squared minus 4x plus 3. Part B says find the values for where the derivative equals 0. Okay, so we have this quadratic function equals 0. There's 2 ways to figure this out. We can use the quadratic formula, or we can try to factor it. I'm going to factor it just because I prefer factoring, but if you use the quadratic equation, that's totally fine too. So when you factor, you're looking for 2 numbers that multiply to give you the last term, but that add up to give you the middle term. So when I factor this, I'm going to have x minus 3, x minus 1. So minus 3 times minus 1 gives me positive 3, but minus 3 plus minus 1 gives me this minus 4. Okay, and so once I've factored it, the reason I want to factor it is because I can set each factor equal to 0. So x minus 3 equals 0. That tells me that x will equal 3 is one solution. And then x minus 1 equals 0 tells me that x minus 1 is a solution, and therefore x would have to equal 1 here. Okay, so there's 2 places that make this 0 at x equals 3 and x equals 1. So those are the values that make this equal to 0. For part C, it wants to know where the original function is increasing and decreasing. So this is where we have to sort of start linking these things together. So remember that we're going to be increasing when the derivative is positive and decreasing when the derivative is negative. The reason I need to find these zeros is because that is where my derivative is going to change from positive to negative or negative to positive. So what I like to do to stay organized is I like to create a number line. You don't have to do it this way, but I think it's a good way to think about it. So I know that the derivative is 0 at 1 and 3, right? That's what I found in part B. So what I want to do is I want to figure out to the left of 1, between 1 and 3, and after 3, whether my first derivative is positive or negative. So I'm going to pick a number to test here. So to the left of 1, I'm going to pick 0, right? I'm going to pick numbers that are easy to think about. If I plug 0 into my first derivative, right? I can plug it in here, I can plug it in here, it doesn't matter. But I'm going to get positive 3. The 3 itself doesn't matter. What matters is that it's positive, because that means that to the left of 1, my original function is increasing, right? Because the derivative is positive. Between 1 and 3, I need to test a number. I'm going to pick 2, right? I'm just trying to pick things that are convenient and easy for me to figure out. So if I were to plug a 2 in here, 2 squared is 4, 4 minus 8 is -4, -4 plus 3 is -1. Again, the 1 part doesn't matter, it's the negative that I'm after. I could also have plugged it into these factors and figured out if it was positive or negative that way. That's fine as well. But here, because the derivative is negative between 1 and 3, that tells me that my original function is decreasing. And then finally, I want to plug in something to the right of 3. So I'm going to pick 4. If I wanted to use the factors, 4 minus 3 is positive 1. 4 minus 1 is positive 3. Positive times positive is positive. So again, what I'm doing here is I'm finding the zeros of the derivative to figure out how to split up my intervals. Then I'm determining if my derivative is positive or negative for each of the intervals I've created. When it's positive, so here, right, I know that my original function, f of x, is increasing. From 1 to 3, my original function is decreasing because my derivative is negative. And then from 3 on, I'm again positive. So I'm increasing. So I'm using those derivative rules and the function to figure out these intervals. Okay. For part D, I'm looking at the second derivative. So I go back to my first derivative from part A to find my second derivative. So here I have x squared. The 2 comes down, so I have 2x. The derivative of minus 4x is minus 4. And the derivative of 3 is 0. So my second derivative is 2x minus 4. The next part asks me where that equals 0. So I set my second derivative equal to 0. I can add the 4 over and divide by 2. And I find that my second derivative equals 0 at x equals 2. And then for part F, I want to know where the original function is concave up or concave down. So again, I'm going to create a number line. But now I'm interested in the sign of the second derivative, because the sign of the second derivative is going to tell me, right, whether or not I'm concave up or concave down. So here, I'm going to test something a little to the left. So I can test 1 and something a little to the right. Right? I don't have intervals because I only have one breaking point. So if I plug a 1 into this function, 2 minus 4 is going to give me negative 2. So that's negative. And if I plug in a 3, 3 times 2 is 6. 6 minus 4 is positive 2. So knowing the sign of the second derivative will tell me the concavity of the original function. So when the second derivative is negative, that means that the original function is concave down. And when the second derivative is positive, I am concave up. So I'm concave down from negative infinity until 2, and I'm concave up from 2 to infinity. So I'm able to use these formulas to start to find these intervals exactly. So that's another one of the main benefits of using these formulas, okay? We're only going to do this sort of lightly for now, but this will come back quite a bit in a few sections from now, okay? So that's just sort of some foreshadowing of what's about to come in a few sections, okay? So another application that we're going to do, we're actually going to skip number 7 because I want to make sure that we get to number 8 really thoroughly, and sines and cosines. But the main application that you are going to have to do on mini quizzes, on chapter quizzes throughout chapter 3 is this example 8, which is find the equation of the tangent line to f of x equals x squared minus 4x plus 1 at x equals 3. And so I want to make sure we spend quite a bit of time on doing this because you're going to see this in a lot of ways. And so we want to talk about how we can use what we've learned about the derivative formulas in addition to what we know about tangent lines to answer this question. Okay, so as a reminder, when we talk about the derivative is the slope of the tangent line. Okay, when we talk about the rate of change, we are talking about the slope of the tangent line. Now, if we are looking for the equation of the tangent line, it's a line, we are going to write this in the form y equals mx plus b. Whenever you're finding the equation of any line, it's going to be in the form y equals mx plus b. So we know from before and from now that the derivative is going to give us the slope. So if I were to find the derivative of this function, I'm going to get 2x minus 4. Okay, that alone is not the slope of my tangent line. The derivative gives me the slope of the tangent line at any point. So I need to figure out what point I am interested in for the scope of this problem. So I look over here and I see at x equals 3. Now that is 1/2 of a point, right? Usually we have an x and a y value. So what I want to do is I want to plug my 3 into the function to get the corresponding y value. I'm going to need that later, okay? If I plug in a 3, I get 3 squared, which is 9, minus 4 times 3. So 9 minus 12 is -3, plus 1 is -2. Okay? So what I'm saying is I am trying to find the equation of the line that touches this function at this point. So at 3, -2, that is the one point that is shared by the tangent line and the function. That's where the line touches. Okay, so I have the derivative, and I want to use this to find the slope. So if I'm looking for the slope at any point, I have 2x minus 4. But I want to know the slope at 3. Okay, so I'm going to go ahead and plug 3 into my derivative function to get the slope at 3, because that's what I want for this problem. So 2 times 3 is 6. 6 minus 4 is 2. So the slope of my tangent line, okay, at the point x equals 3, the slope is going to be 2. So that means that so far, I have y equals 2x plus b, because I can fill in that value for n. Now, I also need to solve for b. How do I solve for b? Well, again, this is the one point that is shared between the function and the tangent line. So I need to plug in this point to solve for b. So my y value is -2. When my x value is 3, I plug those in. 2 times 3 is 6. I subtract 6 to the other side, and I get b equals -8. So finally, I put this all together, and I get y equals 2x minus 8. That is the equation of the tangent line to this function that touches at the point 3, -2. So, quick recap of the steps. We needed to find the point where the line touches. We do that by plugging in the independent value into the function and getting the corresponding dependent value. That's our point. We also need the slope of our tangent line. We find that by finding the first derivative in general and then plugging in the x value of where we want to know the slope of the line, right? If we did it for a different x value, it would change everything in this problem. So we plug in the value that we're interested in to get the slope. Once we have the slope and the point, we put that together in y equals mx plus b to get the equation of the tangent line. Now, like I said, this is a problem that's going to come up a lot in this class, and what will change is the function, right? So as we learn different types of functions, you'll get different functions to do this on, but the equation of the line should always be in the form y equals mx plus b, okay? So the next set of rules that we want to add here are the derivative of sine and cosine. So we're going to add these to our list of rules. And it turns out that if you take the derivative of sine, you get cosine, right? And you do that by looking at the value at every single point and drawing it like we were drawing in chapter 2. And then from there, we recognize that it's cosine. And if you were to take the derivative of cosine, you are going to get negative sine. Okay, so these are directly related. And what we really need to remember is where the negative comes in, right? So the derivative of sine is cosine, but the derivative of cosine is negative sine. Okay, so we add those to our list of rules, and we want to do a little tiny bit of practice with sine and cosine. We will skip example 9. I think example 10 will be more important because, again, it's a find the equation of the tangent line. So what I would like you to do is I would like you to take 2 minutes and try to practice that process that we just discussed of finding the equation of the tangent line, where now our function is 3 cos x. So you'll have to use the constant multiple rule. That 3 is going to come with us. You're going to have to do the derivative of cosine and the process of the tangent line. One word of caution. If you are plugging things into your calculator because you don't know the unit circle, you need to make sure it's in radians. If you try to plug it in and it's in degrees, you'll get the wrong values. Okay, so try it out. See if you can come up with the equation of the tangent line. I'll give you about 2 minutes and then we'll go through it together. Take about 30 more seconds. All right. So again, in order to find the equation of the tangent line, we need a point and the slope. In order to get the point, we plug pi over 2 into the original function. So we have x equals pi over 2, and cosine of pi over 2 is 0. So that gives us the point x equals pi over 2, y equals 0. So that's our point that we're working with. In order to get our slope, we need to use the first derivative. So the derivative of 3 cos x is going to be negative 3 sine x. So technically, we would be doing 3 times negative sine x, but we almost always pull the negative to the front. But if you wrote it as 3 times negative sine x, that's the same thing, okay? So to get the actual slope, we need to plug in our x value into the derivative. So we plug in a pi over 2. Sine of pi over 2 is 1. That's the value from your unit circle. So negative 3 times 1 is going to give me a slope of negative 3. So far, I have y equals negative 3x plus b. Now I need to plug in my point to solve for b. And something interesting and important happens here that we need to talk about. So we have y equals 0, x is pi over 2 plus b, okay? So pi is an irrational number, right? It goes on forever and ever. And so we do not want to convert it to a decimal, because if you change pi from pi into a decimal, you turn it from an exact number into an approximation. And we always want to keep an exact number unless we are told otherwise. So if you have an e or a pi, you never want to turn that into a decimal unless the problem says, like, plug this in and round 2 decimal points or something like that. Otherwise, you need to leave that as pi. So to solve for b, I need to add this term over to the left. So that's going to give me that b equals 3 pi over 2, right? It looks a little strange to have the pi in there, but we need to leave it this way. So now our equation becomes negative 3x, so negative 3 was our slope, plus 3 pi over 2, okay? So that is the equation of our line. 3 pi over 2 is a number, and it is represented correctly because we wrote it exactly. So that's what the equation of our line looks like. Now, if you were plugging things into sine and cosine and getting different values, you either need to change your calculator to radians, or your calculator might be doing some sort of approximation that's really close to 0 and 1. So that's something worth asking at drop-in help if you're not getting the same values, okay? So that is enough for today for what you need for your mini quiz. If you're interested in seeing the work done out for example 8, I think is when we skipped, and then 9 and 11, those are linked in the asynchronous video on Moodle. Okay, I will see you guys on Thursday, and I hope you have a good rest of your day.